Hi, so today we are going to talk a little bit about resistance and how we calculate resistance. And we're also going to talk about circuit rules. There'll be a separate video that shows you the sort of mechanics of how to calculate and do the actual math. This is just to kind of lay out the basic rules for how we approach circuit and circuit math. So let's just take a minute here and let's remember a little bit about resistance in a circuit. Remember that resistance is the hindrance to the flow of charge in a circuit. It's anything that kind of gets in the way or tries to slow down the flow of charge, the flow of electrons through the circuit. Remember, electrons, they don't have just a straight, easy, empty pathway through a wire, let's say. As the electrons are pushed and as they move, they're really kind of bouncing back and forth, and they're colliding and hitting the atoms in the material that they're trying to move through. And all of those atoms are kind of bouncing around or vibrating, and all of that vibration, it's kind of like, you know, being in a really crowded concert where you're trying to move around and you just keep bumping into everybody. That's what resistance is, or trying to walk down a really long hall and the hall is totally packed and every direction you turn it seems you're bumping into somebody and it slows you down. That's what resistance is. Remember that we use the symbol of the ohm, and that's our unit, and our symbol is that omega, which is that kind of curly Q symbol on the screen there, and that is a Greek letter. It's the omega, the last letter of the Greek alphabet. And the other thing I kind of want to say before we get into the actual kind of rules for circuit and how to calculate resistance and all that is that I want us to start thinking about a circuit as a system, okay? And remember, in a circuit, we have to have several things. We have to have some sort of energy source. For most of the time we're usually talking about a battery. We have to have some sort of load. And a load is something that provides resistance in the circuit. And you have to have a conducting material that kind of ties everything together in a continuous conducting pathway. And if we stop and kind of think about the relationships then between those three elements, between what's going on with the energy source pushing the electrons, what's going on with the load elements that are resisting the push of those electrons and maybe even resisting them in such a way that they're taking some of that electrical energy and turning that into, sort of shifting that into something like light or heat or motion like in a motor. And then we think about the electrons themselves that are moving through the wire, which is the current. All of those things are related to one another. How much push there is going to affect the rate at which the charge is flowing, which is the current. So the voltage, or we're going to put that little delta in front of the voltage, the V, and we're going to say the change in the voltage of the energy source, the battery, is going to create a certain amount of push. More push is going to tend to make, you know, the electrons want to move faster. And the more resistance you have, that's going to make the electrons want to slow down because they're having a hard time getting through. And so the next day and a half or so, we're going to be talking about how do these three elements in a circuit, how are they connected with one another? And we're going to go into a little bit of math for that. One last thing before we move into the circuit rules themselves. There are many factors that affect resistance, okay, and how much resistance is present in a material or in a circuit. A couple of just real basic ones. If we're looking at a circuit made of some sort of conducting wire, let's say it's copper, the length of that wire matters. The more length you have to kind of push those electrons through, the more resistance those electrons are going to encounter. It's kind of like trying to run through a hallway that's packed with people and you have to run 100 yards, the length of a football field. as opposed to running a couple of feet where you can kind of bust right through. The area, the cross-sectional area of the wire, which means kind of if you look at the wire end on and you just look at that sort of circular area, that matters too. The more narrow a wire is, and the more narrow it gets, sometimes we'll actually change the kind of width of the material, the diameter of the material, the more resistance you're going to have. Because it's kind of like squeezing the flow of a current of water down. If you squeeze the area, not as much can get through. And so you get more resistance and things kind of back up, and that was part of the video, I believe, that you watched the other day. And finally, that conducting material matters. Is it copper? Is it aluminum? Is it something else? So every specific element, every metal, every material has a conductivity. How easy it is, how much resistance it puts up to the flow of electrons and charge through it. Now, having said all of that, let's take a look at some of the rules for kind of how the different elements of circuits work. Now remember, there are a few different types of circuits. We have series circuits and we have parallel circuits. And then you have kind of a combination circuit that has some series elements and some parallel elements, and we'll get to all of that. But we have a different set of rules for series circuits as we do for parallel circuits. So we're going to take them one at a time. On the screen right now, you're going to see the basic circuit rules for series circuits. Remember, a series circuit is when there is only a single pathway that the electrons can take from one terminal of the battery the whole way around the circuit and back into the other terminal of the battery. The current goes through every element in the circuit, and if you break that circuit anywhere, if you unscrew a bulb, if you cut the wire, if you flip and open a switch, then everything turns off, okay? And the circuit will not work at all. Now remember, we have these three elements. We have our voltage, which has to do with, how much push there is on the electrons to make them move. We have the current, which is how much flow do we actually have in a given amount of time. So we have a rate of flow of the current or the electrons through the wire. And then we have the resistance. How much kind of pushback is there? How much hindrance to the flow of those electrons is there in the circuit? And here's how our rules work. The total voltage of a series circuit is just the sum of all the voltages across all the components of the circuit. So if you have 3 voltages, then you would add those 3 voltages together, and that would be your total voltage for the circuit, okay? And your circuits might be labeled with some parts of that, all right? And you're seeing an equation there, which is delta V equals IR. We'll come back to that in a little bit. Now, in terms of current in a series circuit, the current is the same through all the different components or elements of the circuit. So the current going into a light bulb is the same as the current coming out of that light bulb, which is the same as the current going into the battery is the same as the current going out of the battery. Everything's the same. There is one current. It applies for all the components in the series. If you know the current anywhere, you know the current everywhere in a series circuit. And finally, the total resistance of a series circuit is just the sum of all the individual resistances. So if I have 3 light bulbs and each of them has their own separate resistance, then that is going to be the total resistance on that circuit. Now we have sort of a different way of saying total resistance of the circuit. We call it the equivalent resistance. And you'll see that R, that large R for resistance with the little sub EQ, that means equivalent resistance. And you can see we are just adding up however many resistors we have. For our purposes in our class, we are going to pretend that the wires themselves or the conducting element itself has zero resistance. And that's not true in the real world, but we're going to do that a lot this year. We're going to kind of idealize situations to make analyzing them a little simpler, okay? So we are just going to look at resistances of elements, things like light bulbs and I'm not sure, motors and or whatever else we're going to put into the circuit itself. These are the rules for series circuits. I will drop this slide into your OneNote so that you have access to this slide. And you should always kind of put these in front of you if you want to make flashcards. Sometimes that's easiest. But it's okay to use the rules, all right? And it's important that you make sure that you kind of figure out before you do anything, which kind of circuit do you have? Because if you're not sure which kind of circuit you have, you don't know whether you should be using these series rules or the next rules, which apply to parallel circuits. Okay, now here are the rules for parallel circuits. When we look at the voltage, which is how much push there is from your energy source, your battery, how much push there is to move the electrons through the circuit, notice that the voltage is going to be the same across every part of the circuit. So if you know the voltage anywhere on that circuit, then you know the voltage everywhere on that circuit. So that's real easy. The current is a summation, meaning the total current flowing from the battery is going to be equal to the sum of all the currents on every branch. So the current on each branch, let's say we have 3 branches on our parallel circuit. Your total current then will be the current going through the first branch plus the current going through the second branch plus the current going through the third branch, and so on, however many branches you've got. Now notice that these two are the exact opposite of series circuits, okay? We've kind of flipped around the rule. And resistance looks different too. So the resistance on a parallel circuit follows this formula. Remember, total resistance is the same thing as what we call equivalent resistance, REQ. And to do that calculation, you're going to take 1 over the first resistor's resistance, plus 1 over the second one, plus 1 over the third one, and so on, however many you've got. And then you're going to just do this in a calculator. You're going to add those up, and then you're going to just take that to the -1 power or divide it, okay? You're going to invert it. And there actually are online some resistance calculators that just do this for you. Eventually, I don't mind you using those. I would like you to do the first worksheet on your own to sort of see the process of doing it, and then if you would like to look up a resistance calculator, you're welcome to do that. Remember that parallel circuits, if one branch breaks, there's always another branch for the electrons to travel through, okay? And when they do, they follow these rules here. So analyzing a circuit becomes kind of like a game, where you kind of have to figure out first, what kind of circuit do I have, series, parallel, or a combination of both, that I've got to use both sets of rules. And then once you figure that out, you have to apply the right rules given the information that you have. So it's kind of like a logic game. I think it's kind of fun to figure all this stuff out. I hope you do too. Okay, so here is an actual diagram of a circuit, and anytime the current has a choice of which way to go, that there's more than one way that the electrons could travel, we call that a junction. And we are going to have some rules for junctions called Kirchhoff's rules that we'll talk about later. But for right now, what we want to do is sort of take a look at this circuit and think about what's actually happening here using our circuit rules. For example, how much would the current through the battery change if I unscrewed one of those 2 identical light bulbs? We're going to assume that light bulb A and light bulb B are identical, they're exactly the same. If I unscrew one of those, making one of those branches not work, what's going to happen to the current? Okay? And so let's take a quick look. What kind of circuit is this? What do you think? Notice that in the circuit, you get to this point right here. I'm not sure if you can see where my cursor is, but it's that blue dot at the top of the diagram, where the electrons can go either to the right or they can go down. That means we have a junction, and that means that we have a parallel circuit because the electrons can either go around the big loop and go through light bulb B, or they can go through light bulb A around the smaller loop. And as long as both loops are closed, they're going through both at the same time. Now our question asks about current. Remember that in a parallel circuit, the total current is equal to the current of element A plus the current of branch B, so we're looking at the current on the branches. So if I say that this has 1 amp of current and this has 1 amp of current, the total current of the circuit is going to be 2 amps. That is current A plus current B. If I unscrew B, however, then all that's left is current A, and that's 1 amp, which would be 1/2 of the original 2 amp current. So if I disconnect the bulb, the current through the battery up here is going to be cut in half. So here is the same circuit, but this time we're going to ask a different question. Let's say I do unscrew light bulb B. What's going to happen to the brightness of A? Do you think it's going to get brighter because I don't have this one screwed in anymore? Do you think it's going to stay the same? Or do you think that it's going to go out too? I'll give you just a minute to think about that. So let's think about this. Remember that we said that the total current going through the battery with both of these screwed in, assuming that the current through each branch was 1 amp, that the total current through the battery would be 2 amps. And then on the last slide we said if I unscrew this, however, if I unscrew B and that goes to 0, that this still remains 1 amp. And this, then the current through the battery becomes 1 amp, 1/2 of what it was before. What that means is that A will stay the same brightness if you unscrew B. It's not going to get brighter. And a lot of people think it will. They'll think, well, that extra current will go through here. But that's not how it works, okay? A battery doesn't supply a constant amount of current, say always 2 amps no matter what, and if you break this bulb, then 2 amps go through this bulb. Rather, the battery responds to kind of the system of the circuit, which puts 1 amp through and allows this to stay the same brightness. Okay, and finally, we have a couple of laws for circuits called Kirchhoff's laws or Kirchhoff's rules for circuits. And one is called the loop rule and the other one is called the junction rule. And they just have to do with what goes on with the voltage and what goes on with the current in circuits. So Kirchhoff's loop rule says that the sum of the voltages, and it says potential differences there. We're going to talk about that a little bit later. The sum of the voltages across the circuit elements in a closed loop must equal 0. So the sum in a loop of the changes of the voltages has to add up to 0. All this means is that the voltages across all the components need to sum to the voltage of the battery or the power supply. And Kirchhoff's junction rule says that the total rate at which a charge enters a junction, the current that's going into a junction or a split in the circuit wire, has to equal the total rate of which charge leaves the junction. The sum of the currents into the junction equals the sum of the currents out. Current in has to equal current out whenever you split the wires. And we will come back and talk more about this, but we're going to focus on the slides that earlier had our circuit rules on them right now.